Ladies and gentlemen, welcome to the Shaw Prize Lectures in Mathematical Sciences 2007 at the Hong Kong University of Science and Technology. We would like to first invite Professor Sy Chen, our Dean of Science and himself a mathematician, to say a few words of welcome. Professor Chen.
Good afternoon. It's a big thrill to me to have an opportunity to be here this afternoon. So on behalf of the Hong Kong University of Science and Technology, it's my distinguished honor to extend our warmest welcome to all of you at today's Shaw Prize lecture to be delivered by Professor Robert Reynolds and Professor Richard Taylor. They jointly won the 2007 Shaw Prize in Mathematical Science for initiating and developing a grand unifying vision in mathematics that connects prime numbers and symmetry. So I believe Professor Chen Shuli later will say more about Professor Robert Reynolds and Professor Richard Taylor, so I leave to him. As I said, I'm a mathematician myself and thrilled to see so many young faces here. I believe it must be the vision of Shaw Prize to bring in the brilliant minds of the Shaw laureates to inspire and enlighten our young people. So you are the future of science, you are the future of our society. So this is a unique opportunity. So I'm sure that all of you will come away today both inspired and informed. So as an appreciation to our two distinguished speakers, I would like to present to them a small gift on behalf of Hong Kong University of Science and Technology. So first, I think this is to Professor Reynolds. We have and then Professor Richard Taylor, please.
Thank you, Professor Chen. Professor Zhang Shuli, our head of mathematics department, will now introduce our first distinguished speaker, Professor Robert Reynolds.
Professor Reynolds, Professor Taylor, students and colleagues. Today, I feel most proud and honored to have the opportunity to introduce Professor Robert Reynolds here. To those of us working or learning in the area of automorphic forms and related fields, Professor Reynolds has been an oracle. For the last 40 years, his profound visions embodied in what is known as the Reynolds program have inspired and guided research in automorphic forms, representation theory, number theory, and arithmetic algebraic geometry. And these are some of the most central areas in mathematics. Now, Professor Reynolds' deep visions have led to spectacular successes in solving some of the long-standing problems in number theory, such as Gauss and Taylor's proof, work on the modularity leading to the proof of Fermat's last theorem. His vision will undoubtedly continue to provide inspiration for exciting research for many years to come. Now, Professor Reynolds will tell us some of that history. The title of his lecture is Automorphic Forms, Geometry, and Arithmetic, Past, Present, and Future. Let's welcome Professor Reynolds.
title of this talk is somewhat pretentious, and I apologize for that. But it did seem to me that the occasion, I mean, in fact, it was for me, the receipt of the Shaw Prize was for me an occasion to reflect once again on various aspects of the subject, which I've thought for about 40 years in one way and another, not continually, but for a great part of those 4 decades. Now, there are several reasons for reflecting once again on the subject and reflecting on it in a general way. Partly because, for me, there are several new ideas, important new ideas that have been introduced and that I simply needed to learn. Also, a number of new possibilities that weren't available before that become available that I wanted to talk about. And there's also one more reason, and that is that I became aware that what I'd been trying to say over 40 years wasn't understood exactly in the way that I intended. And so some things apparently I didn't say well enough the first time. So I wrote a lecture entitled Reflections on Receiving the Shaw Prize, in which I tried to review briefly, I think I had 3/4 of an hour in which to talk, its various aspects. Now, I was thinking of people with some mathematical training, perhaps not more than that available in an ordinary graduate school education. But now I understand there's a large number of people from high school here. And I think ultimately you'll discover that this is not really a lecture suitable for high school students. But there is something to be said. I'm dealing with what could be regarded as modern mathematics. Modern mathematics even is something that is already 200 years old, even a little bit more. And there's a tradition, and it's a cumulative tradition. I do not think that someone working in the beginning of the 21st century can do it independently of what happened at the end of the 18th and the beginning of the 19th. The inspiration that was there in the beginning still inspires today. So one thing you may learn, and one thing I may emphasize by just adding a few words of preface about the beginnings of the subject, is that mathematics is, unlike many other sciences, is a science that's attached to its own history and that is dependent on its own history. So the things I talk about immediately are things that you can begin to learn now. You probably need the correct teacher, but that you can begin to learn now. The things that I talk about at the end, you can't begin to learn now. You need some experience. Now let me begin with a modern diagram, just so we can have it as reference. I think someone has the text. I sent the text to Stephen Kong, so it may be available if you want the text of the lecture, which is a preliminary form. In fact, you must understand that this is the first version of these reflections that I promised. I think they're brief and they're rough, and they include many ideas on which I haven't had adequate time to reflect, some things that I don't understand at all. But the preliminary version would perhaps be easier to read, although difficult than any final version. And let me write a diagram. That won't mean anything at all at first. It has a diagram, with, I'll make the circle just a little smaller. It's a schematic representation of the subject. In this most of these circles you won't know anything about now. You may at least know the historical background. There's a second one says function fields over finite fields. Don't worry, let me get this all down before I begin to explain. And then over complex fields. And then there's another circle, Galois representations. And final circle, well, there are also arrows relations here. And this is really what I would call Grothendiekian. Grothendieck, by the way, for those who aren't mathematicians, they're just students, was, in my view, perhaps the greatest mathematician of the second half of the 20th century. Grothendiekian algebraic geometry. And what are called motifs. And the central arrow is perhaps this one, but what I want to, I'll come back to it. What I want to stress, what I want to point out, is that this subject has an independent existence. It's an autonomous subject, independent of this. The main connection is here. Often by the intermediate, by the mediation of Gauss representations. And as I'll point out here, these have grown out of that. This is the theory, basically, of Riemann surfaces and ordinary differential equations. And there's a strong relation. The relation between these three subjects probably doesn't just go in one direction, it goes in both. But let me begin now with reminding you of some historical facts. When did this whole subject begin, really, and what did it begin with? Well, insofar as it had to do with numbers, I would say it began in 1797 with Gauss. And what I want to point out, first of all, is that if you have a teacher, a competent teacher, then you can read Gauss. A good part of Gauss's famous researches on arithmetic there. Concrete and elementary. If you just open the book, you won't know what he's saying. But if you have someone to help you, then you'll know what he's saying. And they are concerned with two things. They are concerned, number theory, modern number theory is concerned largely with two things, arithmetic, irrational numbers. So simple irrational numbers, those known to the Greeks like that, or more complicated irrational numbers such as the roots of unity, solutions of this equation. So e to the 2 pi I k over n, where k is an integer. So these algebraic numbers are really extremely complicated, but simple. They're accessible, very elementary level, and you can find in Gauss the theory of that. And once Gauss began, so that was Gauss, then they're irrational numbers, and their factorization into primes. So the word ideal comes up. And that's a long sequence of names. I want to start with just some of them. It began with Gauss, and then there are people. There's a 19th century German mathematics consisted of this. Dedekind, and we can go on. And the last great representative was Artin in the 1920s. And I want to point out, that this is already a very elegant subject. You will find in a recent issue of the Notices of the American Mathematical Society 2 articles with serious defects. And one is about comment on the development of the theory of prime ideals. It's a review of a book. I haven't seen the book, but the poor author has clearly just tried to describe Dedekind's own notion of what he was doing when he created the theory of the prime factorization of irrational numbers, which just doesn't look in the hands of Dedekind. And he's clearly just repeating what Dedekind himself explained, what Dedekind's own notion of prime numbers are. But the reviewer of the book had an education, obviously, in an American university. All American universities are no worse than others. And he sort of laughed at the author, at this silly expression, this silly explanation of what a prime ideal really is. What are the objects that allow for the factorization of numbers like those derived from this equation. And so, without knowing it, the reviewer was simply laughing at Dedekind. And it was rather dismaying to see that in a journal which is probably the most widely circulated mathematics journal. Anyhow, what Artin, see these numbers, for those who've heard the name Galois, are related to, have symmetries, and the theory with Artin, as it reached Artin, was a theory for abelian symmetries. Artin somehow had the germs of a theory for non-abelian symmetries. So 1920, some sense, not quite true, but the theory for abelian symmetries had reached a very mature state. The impulse was to create a theory for non-abelian symmetries, and but in the 1950s, Artin was suggesting that there was no theory for non-abelian symmetry. And so the situation that existed when I was young in the 60s was a situation in which there was pessimism on the part, Artin was by then dead, but Artin had not very long before expressed a great deal of pessimism about non-abelian symmetries. And what was proposed was, to some reflection, a lot of reflection, and a lot of sweat, I managed to propose was a possibility for the theory for non-abelian symmetry. Now, so that's one of the things that has become the object of discussion, about which people have thought a great deal since 1960s, and which some progress has been made, but by no means as much as we want. And so that's one of the origins of modern number theories, the study of these irrational numbers and their decomposition into primes, and decomposition like the decomposition that you know for ordinary integers into primes. The second one is geometry. Let's say, as we know, with algebraic geometry. And here, I mean, the paper to read, in some sense, written in the first part of the 17th century, is Descartes' article on geometry. But in contrast to the article of Gauss, you can't read Descartes on geometry and know its connection with 20th century or 21st century geometry without knowing 20th century geometry. But once you know 20th century geometry, it's fascinating to read Descartes. The modern major figure in geometry is Grothendieck. All right. And then there's a third topic, and this is a third topic about which you will have heard nothing, and in which I fear, about which I fear not too many people know something. It's the subject which is abstruse because it involves not only algebraic numbers, but it involves as well analysis, harmonic analysis, the usual harmonic analysis is that on the line or the circle, but harmonic analysis it involves is that on non-compact, non-abelian groups. And what that means in concrete terms for those who have some experience in mathematics is that you have to create for specific families of commuting differential operators a simultaneous spectral decomposition. And I would say that it's a kind of mathematics which is, of course, related to the spectral decomposition of a single differential operator, but which is shunned by and large by analysts, because it also entails too much algebra, and the key to this problem seems to lie here. Just to give you some idea, just observe that this subject, in spite of the fact that we're talking about non-abelian, non-compact groups, really has also its origins in the original researches of Gauss. Gauss's book on arithmetical researches was about more than one thing. And this was about forms, if you like, in two variables, x and y, with integer coefficients. Gauss began the study of that. This study by Gauss went on not so intensely as the study of irrational numbers or prime ideals throughout the 19th century. And then there were several people in the middle. There were people like Minkowski and Eisenstein and actually J.H.S. Smith, then Hardy Littlewood, and in the 20th century, Carl Ludwig Siegel, Hecke, and Selberg. So what we see here is that this is a theory which was largely analytic and is closely related to analytic number theory. So this is a topic. I have to talk about this topic, and I have to talk to you about it without really telling you what it is. And the final thing that enters into this subject are L functions. So this is an infinite sum. They're like this. This is the Riemann zeta function. It's a famous function, not all of whose properties are yet known. All right. Now, what is, I said, here, the idea, what's sometimes referred to, although I don't use this word myself for obvious reasons, the Langlands program, what it offers is at least at first only conjecturally, but with some real results, solution of two problems, namely the formulation of what a non-abelian analysis or what a classification of non-abelian irrational numbers might be, and at the same time, I hope that this demonstration on the left is not more exciting than this demonstration in the middle. All right. Wants to do two things. It wants to analyze the non-abelian, the algebraic numbers with non-abelian symmetries, and at the same time, it wants to create the most general class of L functions. So those were two problems that actually were there for young people to think about in the 60s. And this one was actually more thought about more intensely and by more people than this one. As I say, this one has been basically abandoned. Now, let me tell you how this solution appears. You won't recognize it. It doesn't seem to be a solution. Let me tell you how it appears. Because at the moment I'm describing, I insist, an autonomous theory of automorphic form. So it has to do with groups. And let's just think. So it has to do with a situation in which I have a group and a subgroup. And this group gamma could be the group of n by n matrices with integral coefficients, integral entries, and G could be the group of n by n matrices with real coefficients. Now, that's a standard situation. This real situation has more arithmetic subtlety in it, more number theoretic subtlety. And then I look at functions on that, so functions f of h on this space, on this quotient space, the cosets of gamma in G. That's a manifold. And I look at the action of G on this, which sends a function of h into a new function, f prime of h equals f of hg. So if any element G in G. Now, what we have to pass over, we have to pass over something which is an extension of ordinary Fourier analysis, namely, it's the analysis of this decomposition of this action into simplest possible actions, and these simple possible actions like harmonic analysis, like the theory of Fourier series, or if you like, it's this very complicated harmonic analysis. Just take it for granted. And the irreducible ingredients, the primitive objects for this analysis are actually representations of this group, G, and they're called automorphic representations. But we're going to work now, I want you to see the formal structure of the theory, because that's all I can explain. And there were two things. Turns out we have this G, it's a group like GLNR. There is associated to G a group of the same dimension, which is a complex group. It's called the L group. And it would be, in this particular case, when that's G complex matrices times a Galois group. So we could take, say, a base field, which could be Q, an algebraic Galois extension, which could be K, and this is the L group. And what I want to say is that if we have pi, very complicated, relatively complicated process, if we have pi and we have a representation of GL, so for example, if n was equal to 2, these would be the group of matrices. So group of matrices act on, say, two-dimensional vectors, x and y, and a representation would be given by extending this action on x and y to an action on three-dimensional space consisting of the polynomials of degree 2 in x and y. And then whenever we have a representation like this of the group GL, then we can define an L function, which is associated to pi, and R, which is the product over primes, if the base field is Q, of 1 over 1 minus R of, which is the determinant, of 1 minus R of A sub P of pi over P to the S. So this looks like the Riemann zeta function, except that this little thing is included. And AP of pi is for each P is a conjugacy class. It's actually a set of conjugate elements in this group GL. So in this case, there would be each of those AP pi's would be an n by n matrix together with an element of the Galois group. That depended upon P. So the problem that these were, for various reasons, there was various evidence that was discovered at the time, that these were the good L functions. There was a good, most general extension of the Riemann zeta function. And then you had to prove them. You had to prove that they behaved like Riemann zeta function. You see, they're a function of this analytic parameter S, so you had to show that the product converged in a half plane, and that then could be analytically continued. And this was and remains a central problem which has been solved in many special cases, but has not yet been solved in general. And so it's one of the core problems of the theory, and I give it the name functoriality. So in the L group. And I think the result was that no one ever tried to understand what it really meant. So in that sense, it wasn't a good name, but although it is a suggestive name. And the problem was to establish it, And what is this functoriality in the L group? We go over here. I'll let somebody else free that blackboard, because this time is, I'll be running out of time before I say anything. It's this. If we have two, we have the group G and we have a group H, and we have a homomorphism from HL into GL, then associated to that homomorphism, there's two groups, is a map from P into a new P sub H, an automorphic representation of H, into the course of something like that for G. So this is in existence there. And if you look closely at what that exists, so that's what we want to prove. And if you look closely at what it means, we can erase that, I guess. Yes, go ahead. If you look closely at what that means, for the case that H is the trivial group, H is the trivial group doesn't mean that HL is trivial because of the presence of the Galois group here. So if you look closely at what it means, you see that it's a solution to Artin's problem, namely the problem of describing. You see that you can't solve it. To solve it means dealing with Artin-L functions and dealing with the problem of the nature of the non-abelian extensions of Q or of any other group. All right. Now, what is, in my view, the sole method of dealing with this problem? The sole method is harmonic analysis. This problem is really a problem in harmonic analysis. It's comparing harmonic analysis on two groups. Remember, these pi's are the basic elements in harmonic analysis. They're like cosine of nx or sine of nx. And that, there is only one method available. It has a very large and complex development, and that is the trace formula, which was originally due to Selberg and then has been extended to groups other than GL2, basically, or others, by Arthur. And it's quite, in itself, a quite important and complex subfield of the theory of automorphic forms. Now, one can do something about this particular conjecture, namely the existence of pi of G given pi of H with the help of the trace formula. And I'll give you a catchword. There's a certain class of phi for which this can be done, and they're caught by the word catchword endoscopy. Now, there are two things that were clear. Endoscopy was introduced in the mid-70s. But there were two things that were quite troubling about it. First of all, endoscopy will not handle the general problem. It will only handle specific problems. It will handle, say, cyclic base change and a few other things. But it will not, one knew that from the very beginning, that it would not handle everything. At the same time, endoscopy posed some very difficult problems. It posed the problem of the fundamental lemma. Now, when I came across the fundamental lemma, which is a combinatorial lemma, quite clear, quite neat combinatorial lemma, I said to myself, as I think anyone else would, combinatorics is easy. All you have to do is understand it. You just have, and actually, I thought about it for a long time. I would say at the order of 10 years, and various students thought about it too, some of them very good students, Rogowski, Kottwitz, Hale, and we didn't get it. So it was an obstacle, and also I should say it was a psychological obstacle. Namely, we couldn't think beyond endoscopy because we were stuck. Now, what has happened, a number of people over the years have thought about this fundamental lemma. Congruence himself continued to think about it and introduced the topological component. And people in Paris, Waldsberger, Lemma, and most recently, a young Vietnamese mathematician, in his 30s, Gauss. And I think it's fair to say they've solved it. That we now have this fundamental lemma. And so we've reached a new stage. I mean, Gauss' work is not completely published. There are forms of the fundamental lemma. And I have been trying to understand Gauss. And I finally realized, just reading them, just trying to understand them, that it's sometimes a revelation what he's done. I had been thinking about these things in the wrong way for years. So I won't say it. So Gauss uses algebraic stacks. Algebraic stacks are basically like algebraic varieties, except you divide it by a group. And then you count the number of points on stacks, and you use their cohomology, and so on. And it's a concept that algebraic stacks just seem to me formal. I never bothered to learn it, and so I didn't quite understand what Gauss was saying for a while. But then I realized that I'd been thinking about the harmonic analysis on groups, harmonic analysis implicit in space form, in the wrong way for years. And so I was just thinking about that at the beginning of the summer, and I wanted to tell you what the consequences are. The whole procedure for Go, there are local questions here. So we're working up on that top circle over number fields. And Waldsberger says, oh, it's all right to go over to function fields over finite fields. And what Gauss says, at least for endoscopy, is that for function fields over finite fields, we're counting points on stacks. But counting points on stacks is, so to speak, a part of the modern algebraic geometry of Grothendieck. It just has to do with analyzing cohomology groups. So, but what does that mean? Well, let's go back to beyond endoscopy. Now here, I'm really talking about things that I hardly know what a stack is. So I'm going to go back and tell you what one does, what it appears that one can do now, but I can't do it yet. I've talked a little bit with specialists in complex fields and also with Go, and maybe it's all right, but it will take a very long time. You see, with beyond endoscopy, there's a paper with that title that I wrote. You basically have, what you get is, what you want to look at is for a given group, you want to look, the limit as s approaches 1 of summation over pi. These are all L prime of s pi r for any r. Remember, this is the representation of the L group. This is Ls pi r. And you want to get that the trace formula. This sort of looks like summation p less than or equal to x log p summation over pi. And if you have this, so you want to get, in order to make the comparison between two different groups, you need to analyze something like that. It's very hard. So you think, well, I'll just move down to function fields over finite fields and see what happens there. Well, it turns out that what you're doing, and you want to show this limit exists, and you wanted to show it has something to do with Galois extensions. Now, here's how it looks. On a very superficial, very slight analysis, of what I said in Beyond Endoscopy in a subsequent paper which is related on endoscopy for function fields over finite fields. This sum is really, I mean, over function fields, summation p less than or equal to x becomes summation over degree p equal to a given number k, and you let k go to infinity. So over function fields, this kind of thing, which is familiar to analytic number theories, becomes something like this. So, and it turns out that what you're doing is counting the number of points on x, on these mysterious stacks. And one knows from the theory from Grothendieck that this is equal to the summation. These objects are algebraic varieties, and they have cohomology. And say the stack is of degree n. These sums like this are basically -1 to the I, and then some trace on the cohomology of degree I. Now, so you just need to know the cohomology. In other words, what you see for GL2, for example, is that you need this to be something simple in degree 2n. You need the cohomology to be 0 between the middle dimension, basically, and the highest dimension, and you don't care because you're dividing by something what happens below. So you need a statement about the cohomology of certain stacks over function fields over finite fields. But, and now I'm just sort of take with a grain of salt what I'm saying, but this is the idea. At first, if I want to see what's happening over finite fields, I can work over C because they're comparison theorems. They're just cohomology. Now, I've ceased to, what I want to do has nothing more to do with counting points. It just has to deal with the knowledge of cohomology. So I get at something over C, and if you look at what you have over C, you see they're related to, actually related to the cohomology you're trying to compute is in some way or other related to the cohomology of braid groups. That's a complicated subject, but much more accessible. That's for GL2, not for other groups. So what we can do now is we can hope that not only we can get through the fundamental lemma of endoscopy, but we now have a handle on functoriality in general. I don't promise anything, but we have some hope. And for 3 decades or several decades, we had no hope. Now, the next step will be, so what I'm saying is, we wanted to handle the problem of monomorphic forms, something over number fields. We go to over finite fields. We understand it better in homological terms. We go to complex fields where the theory is, I mean, over complex fields, that's the theory for if you're a physicist that Witten is talking about. And the theory of ordinary differential equations. So you go there, you prove something there about the cohomology of these complicated objects. It pulls back up to the second circle, and then you know through the second circle, you still have to go back to the first circle. Yet, in other words, you have to somehow get back to number fields. Now here, it's not clear what to do. I mean, my hope is just that if you can work through the theory for finite over finite fields, then you'll see enough, and you'll see what the analytic problems are, the problems of analytic number theory, that you can get back up to the first circle there on the left. But you won't be able to do any of this until you finish the work over the middle part. And as I say, this is just something that I began to reflect on reading Go. So that's somehow the proposal for an autonomous theory of function fields over finite fields. And for over automorphic forms, but we have a long way to go. But nonetheless, I think now we see how to work, where to go. Now, I want to say something about, you see, if we have this theory, once we have functoriality, then we have maps. We have a phi here. We have it here. And so we can begin to think an automorphic representation is not something attached to a particular group. It moves from group to group And in particular, you see, once we have a theory, there will be a the smallest group, because we can keep pushing it back from a big group to a smaller group to an even smaller group, and then somehow or other it will get back to the smallest. So in some sense, it will be in there in a thick way. So there'll be, eventually we get to a point where we can't make h any smaller, and then we could factor h into irreducible component, and it will be thick. And then what will that mean? And so that is a part that we'll have to prove too, and that means that every automorphic form basically will be associated to a group in which it's thick. And so, but this group may be a product, so we can take one of the factors. So we pass from h to a factor. And what I want to say is, once you achieve that, then the eigenvalues of the Heck operators are distributed for that automorphic form. They're going to be necessarily, for this to be thick will mean that L of S pi of R basically has no pole at S equal 1 unless R is trivial. If R is irreducible, it has no pole at S equal 1. If R is trivial, then it has the pole 1. So you're working back to a situation where you see that where you get this, every automorphic representation is somehow can be pushed back to a smallest group that can be factored, and then it sits on an irreducible group. And then, of course, if you can do that, then you know everything you want to know about the distribution of the eigenvalues of the Heck operator. And you have a stronger, you don't just know the asymptotic values, you know something more. Their asymptotic values, I point out, is, roughly speaking, for the people who know, the relation between Chepetarov and the Artin conjecture. In other words, Chepetarov is a weaker state, proved it before the theory was proved at the very beginning of the development of class field theory, and is a much weaker statement, or at least a weaker statement, than the Artin conjecture. And this is true in general. You can have the Chepetarov theorem in general is, I think, fair to say, the tetrastate conjecture in general. But this is, the Artin conjecture is somewhat stronger. And not only that, what I need to insist again here is that there are two kinds of automorphic forms, as you will see. Those that correspond in some sense to Galois representations, and those like mass forms that can't. And insofar as you're working within the theory of automorphic forms, every theorem has to be proved in some sense, ultimately, for those that aren't related to Galois representations. I'd like to insist upon that. That is part of the autonomous nature of the theory of automorphic forms. Now, I have very little time, but there are two things I want to observe. So, in my view, now the people who, like myself, who've basically been not entirely, but largely interested in this autonomous theory, have a lot to face in the study of Galois representations. Basically, I mean, since the proof of Fermat by Taylor and Wiles, I mean, since the various developments by Taylor and other people, theory of Galois representation, there's also more purely the work unrelated to automorphic forms of Fontaine. There is a local p-adic Langlands correspondence that also comes in, but somehow all that is now part Galois representations. But for me, one should really think in terms now of the correspondence, assuming that one has handled things for automorphic forms. This is the way I think when Richard Taylor said yesterday, I didn't entirely approve of everything. He meant this, that I was attached to a strong way to automorphic forms and an autonomous thing. So, and what I would like to see, and what I would like to think about, although probably never do anything, is the following. There is a small collection of automorphic forms and a small collection over here of motifs for which one understands this arrow. And that is those things of CM type. potentially CM type. I won't tell you what that is. There are things which are basically abelian, for which these groups H that arise are basically abelians or tori. And there one really has a candidate for a correspondence about which everything is known. And then I'm curious. I've asked, Richard Taylor is probably getting fed up with the fact that I keep asking this question, but I haven't thought about it yet, whether how much from the theory, the strictly algebraic theory, how much can one get from that assumption, namely that you have functoriality, you have the natural theory for CM, things of CM type, and you know everything that Richard Taylor and others know about Gauss representation. How far can you get in the correspondence for the upper arrow? Now I've almost finished taking up almost all the arrow. The real arrow, however, is the diagonal arrow. All right? The real arrow is the diagonal arrow. And I want to say something about, I want to recall that when Deligne proved the last of the four Weil conjectures, Grothendieck was troubled. He was troubled because Deligne seemed to avoid the constructing a theory of motifs, which I think was a cherished dream of Grothendieck. But if you look at it, you see he could have reacted in another way. The essence of Deligne's proof consisted of two things, I think. He knew Grothendieck's theory of étale cohomology really much more profoundly than anyone else, maybe even much more profoundly than Grothendieck. And he had an observation. He knew from an observation in the context of automorphic forms that from functoriality you could deduce the Riemann-Ujjan conjecture. He also knew, of course, that there were theories that in the context of the Weil zeta function, you had this functoriality, and you just had to put together all you knew if you happen to know it all, and perhaps only Deligne knew it all. So a conclusion that you might have drawn from this is not that it's unfortunate that we didn't use the theory of motifs to prove the last of the Weil conjectures, but perhaps we should try to handle automorphic forms and motifs at the same time. Motifs, I should say, are objects that people can't quite define. I mean, you have to think of them as 20th or the 21st century's conception of ideal numbers. They're ideal objects, but I think they're even harder ideal objects to get at than the ideal numbers, because there are a large number of problems in algebraic geometry tied to them, in particular the Hodge conjecture. So if one says, this I don't know, I really don't have any ideas, but we should really get at the motifs that we're trying to associate with a certain class of automorphic forms in the context of that relation. Then there's an I was talking to Harder on my vacation, Gunther Harder, we were on vacation together. There's, first of all, an interesting question that arises, and that I offered you. This correspondence would only be valid for motifs that were defined over a number field. There are motifs defined only over transcendental extensions of Q. So the question that one might ask is the following. If one knows the Hodge conjecture for varieties defined over number fields, can one possibly deduce it for all varieties? Now that's a question that I observe goes counter to my philosophy that automorphic forms are autonomous, that you should be able to deal with mass forms as well as the so-called arithmetic forms. Because what I'm suggesting at the other side is that maybe it's enough to deal with motifs that come over Q. I don't know, but it would be nice if one could construct a theory along those lines, which understand more about Gauss representations and somehow work along the back and forth along the diagonal arrow, and get at the same time from a complete theory of automorphic forms the correspondence and the theory of motifs. So that was, you don't take anything I said seriously, but if you're young, you might try to find a good teacher, either here in Hong Kong or elsewhere, and who can guide you through this mess of problems. Okay, I noticed that you're thinking I'm at an end, and I am at an end, but I would like to say that there is one additional problem, two, but there's one additional problem that I really want to mention, and that is the real question, the hardest question, I think, for young people in this whole thing, what are the real number theoretic consequences of this elaborate architecture? That, I think, is hard. I mean, one knows that Fermat's theorem is a relatively simple consequence of the elaborate architecture. Are there other elementary number theoretic consequences that you would value if you could prove them that result from this? I don't know the answer. In some sense, Mordel's theorem also is part of this architecture. But whether there are more, I have no idea. I think it's a problem question what we're thinking about. Anyhow, thank you very much.
Thank you, Professor Reynolds. We can entertain a few questions.
I'll let you take the questions. I'll answer them, but you take them. No, I'll answer, but you have to tell me which question to take.
All right. Okay. Is it possible, or can you give us intuitive or philosophical or daily life or naive description about the subjects, different subjects you give us today, such as the finite fields, automorphic forms, and the quantitative geometry. Okay.
Yes.
Intuitive one, okay, so that we can, is any in a couple of sentences?
Well, as I said, the best, I don't think there's an intuitive one, right? One can read Descartes, and one can certainly read Gauss. And my advice was rather, in other words, in order to begin in this subject, it's probably not a good idea to try to find even an intuitive picture of what I'm trying to say. It's probably best to go to Gauss to see what Gauss said to find out what irrational numbers are, to go to, say, Arbol, and to find out what an elliptic integral is, right? And I haven't said anything about the relation of this bottom circle to ordinary integrals of algebraic functions. My advice to anyone who doesn't have some familiarity with integrals of algebraic functions, such as dx over the square root of x cubed minus 3, he should go back to Arbol, later paper, and find out what those are, and Gauss, and find out what a cyclotomic number is, and then come back. Is that, and I think a sentence, I mean, I gave a sentence, I said, it has to do with algebraic numbers and like roots of unity. I don't think I can say much more. And I said at the end a problem too, namely, this is a very elaborate architecture with very few concrete results, but those concrete results are so striking, like Fermat's theorem, that one has to take them seriously. Fermat's theorem is something you know. Yes, all right.
We can take one or two more questions.
You say something like a competition, like this converse theorems and also this geometric thing. Can you maybe, so this is actually a technical question.
Yes.
So there's things like your so-called the competition to endoscopy, like converse theorems, and then there's things like geometric. Can you maybe put that in a broad?
All right. In other words, my view of converse theorems is, I would say, generally they're provisional. They've been converse theorems, I should say, can be thought of as ways of proving particular cases of functoriality. And the proofs are somehow quite hard. I mean, they involve developments over a long period of years, but they were proofs that had limits. Right? In these proofs, it was clear they weren't going to get the general statements you want. And on the other hand, they've had, I think, an enormous influence on analytic number theory and on this subject simply because they persuaded they have analytic number theoretic consequences, the converse theorems, and these consequences have persuaded analytic number theorists that functoriality has something to offer them. But I think that converse theorems as such are somehow an anomaly. I don't know about you. I mean, we haven't talked about quadratic reciprocity here, but quadratic reciprocity is a theorem with 150 or something proofs. But I would say that there's only one proof, and that's real fact that quadratic extensions are contained in cyclotomic extensions. In other words, all the others are kind of tricks, it seems to me. But there's only, and that functoriality is a little bit like that. There are tricks, but these tricks, it's a certain set of mind I regard as deceptive. When I was young, there was a view often expressed by Sy Chen and others that when God made the universe, he gave the devil free rein except for a certain number of principles that must be obeyed. And I think in a subject like this, you really see the devil at work in the large number of trails that only go part way. But Sy Chen is not here to discuss this philosophy.
Last question.
I'm actually an engineering student, but in my spare time I try to get hold of as much of Kepler's, Leibniz, Gauss, and Riemann's writings as possible. To my impression, it seems like their approach to mathematics, specifically Kepler, for example, with this harmonic ordering of the solar system, has been in contemporary mathematics, especially through the positivist branch in the 20th century, ridiculed and considered irrational and so forth. Do you think we have to go back to some of that tradition, what is considered the metaphysical tradition in mathematics, to understand these problems better?
I guess to answer your question honestly, I don't know Kepler. And I think it's useful to Gauss or Dedekind or Kronecker. And I find it fun to read Descartes, but and I find it useful. You learn a little bit about mathematics and mathematicians on reading Descartes and comparing him, say, with Fermat on the same subject. But I've never gone back to Kepler, and so I'm sorry, but I really can't answer that.
So as you know, the next talk is by Professor Richard Taylor. He will be using transparencies, and we'll take a short break, and the next talk will resume at 4:20. And before we leave, let's thank Professor Reynolds again.
Work up there. Sorry? Work up there. I hope you.
All right. We'll begin our second Shaw Prize lecture this afternoon. It is my great pleasure to introduce Professor Richard Taylor. Those in number theory know of Richard Taylor almost as soon as he's out of graduate school. But to the broad scientific community, he became well known in the middle 90s when he helped Andrew Wiles completing the proof of Fermat's last theorem. In the last couple of years, Taylor has been one of the main driving forces for research in number theory, with a string of spectacular successes, starting from his proof with Michael Harris of the local Reynolds conjecture, and then impressive new advances in the Shimura-Taniyama conjecture and the Artin conjecture for two-dimensional Galois representations, and most recently, the proof of the subtle theta conjecture. In his short lecture today and his IS lectures 2 days from now, Professor Taylor will explain to us some of these breathtaking breakthroughs The title of his lecture today is Reciprocity Laws. Let's welcome Professor Taylor.
Thank you very much. Now let me see if I can work these. Yes, let's try both of them, yes. Okay, well, I'm going to take a very different approach from Bob's to a similar subject. Instead of trying to describe the grand architecture of the theory, I want to concentrate on a few concrete examples and try and explain them, and through those concrete examples maybe convey something of how a more general theory might look like. Be very elementary, I hope. I'm going to use little more than some familiarity with equations, but you will need to concentrate. If I'm going to say anything, I'm going to have to introduce a few terms, and you're going to have to remember them, and we will use them later in the lecture. So it's a bit like a class. The first term, maybe these will be familiar to a lot of people. The first thing I want to remind you is about prime numbers. These are numbers bigger than 1 that are divisible only, exactly divisible only by 1 and themselves. So numbers like 2, 3, 5, 7, 11, the only numbers that divide 5 are 1 and 5 itself. That's a prime number. There's a sequence that I've written on the slide here. It's an infinite sequence. And then there are other numbers, the numbers that I've left out, the composite numbers. Take a number like 6, it's divisible by 2 and 3, so it has more factors. And the primes are very much the building blocks of all the numbers. One way of expressing that is that every whole number can be uniquely written, essentially uniquely written, as a product of prime numbers. So, say that here, for instance, I chose 204. So it's the product of 2 by itself twice, and 3 and 17. It's exactly general property. And number theorists very much focus on prime numbers because within them is packaged the core, the most essential part of the question. So that's the first of the concepts I want to either tell you about or remind you about before I really get going. The second are called congruences. So two whole numbers, called on this slide A and B, are congruent modulo another number P, simply if P divides the difference. And I write A is congruent to or equal to B modulo P. Mod, short for modular. So, for instance, some very simple examples, maybe. Over here, we can keep two things going at the same time. 2 is congruent to 17 modulo 3. That's simply saying that if I take 2 and add 3 to it 5 times, I end up with 17. Modulo 2, there are 2 congruence classes. Any even number is congruent to 0, and any odd number is congruent to 1. So the congruence class is modulo 2 is simply the odd-even distinction amongst whole numbers. Another example, 1 is congruent to 13 modulo 12. 13 is simply 1 plus 12. The difference is divisible by 12. And congruences are sometimes given the name clock arithmetic for this sort of reason, that if when we tell the time, we work modulo 12. The hands of the clock after 12 hours come back to the same place. And what's 1 o'clock in the afternoon is often referred to as 1300 hours. It's because when we look at the clock face, we're working modulo 12. They're the same you go around. But there was no particular reason why one has 12 hours from midnight to noon. One could imagine clocks with any number of hours, and that's exactly what this process of congruences is. So here I've imagined a clock where there were 7 hours. We have 0, midnight as it were, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, and then when we come back, we're working modulo 7, the 7th hour, the hour hand comes back to the same position, and I'm going to treat 0 and 7 as the same thing. And I can keep going. So here I've written a sort of minimum positive representative of each of the hour, and then listed some of the other things that are to be thought of as the same when I'm working modulo 7, when I'm studying congruences modulo the number 7. Well, I can do arithmetic in this world. Some examples of arithmetic. So, for instance, 5 plus 6 in this mod 7 world is 4. If I start at 5 o'clock, as it were, and add 6 more hours, 1, 2, 3, 4, 5, 6, I come to the hour labeled 4. Or put another way, 5 plus 6 is typically 11, and if I take 7 away from that, I get 4. And then I've written some more simple sums, 3 minus 5. So if I start at 3 o'clock and subtract 5 hours, count back 5 hours, 1, 2, 3, 4, 5, I get 5. So in this mod 7 world, 3 minus 5 is to be thought of as 5 again. And equally, I can do multiplication. I've given a list there of the squares in this mod 7 world. So if I take 3 lots of 3, then I claim I get 2. So 3, 1, 2, 3, another lot of 3, 1, 2, 3, another lot of 3, I end up at 2. So 3 squared in the mod 7 world is 2, and I will shortly come back to this table of squares. We're not limited to doing arithmetic. We can also do algebra. I can consider equations in this modular world, 7 world. I can, for instance, consider the quadratic equation, maybe the simplest sort of equation, x squared congruent to 2 modulo 7. Does 2 have square roots in this mod 7 world? We know it doesn't in the integers or the rational numbers. And if we look at this list, we look down for something that squares to 2, and we find 2 solutions. So 3 and 4 are the 2 square roots, there turn out to be exactly 2 square roots of 2 modulo 7. On the other hand, x squared congruent to minus 1. Does minus 1 have a square root in this mod 7 world? No, it doesn't. If I look along this list, I know where, well, minus 1 modulo 7, 7 minus 1 is 6. I'm looking for a 6 in this list of squares. It never occurs. No reason to restrict to quadratic equations. One can look at, for instance, cubic equations is the next simplest. If I look for cube roots of 1 in this mod 7 world, there are 3 of them, 1, 2, and 4. Again, it's an easy calculation to check if you want to. And one can look at equations with more than one variable. Or indeed, one could look at simultaneous equations, but I'm going to stick to one equation in this lecture. So here I've written the equation y squared plus y equals x cubed minus x squared. One can, without great difficulty, tabulate all its solutions. Maybe the simplest thing is to let x run over the 7 possibilities, 0, 1, 2, up to 6. Each time we calculate the value of this, and then we have a little quadratic equation to solve. For instance, maybe the simplest is to tabulate solutions in y. I've done that here. There are exactly 9 solutions, I think. 2, 3, 4. Exactly 9 solutions which I've listed here. X, y could be 0, 0, 0, 6, and so on. So in this mod 7 world, or indeed modulo any integer, though we will stick to looking modulo prime numbers, which seems to be the most interesting case, one can do all of arithmetic and all of algebra in this way. Okay, well now I come to the title of my lecture, which is Reciprocity Laws. What are reciprocity laws? they asked us to fix an equation or a system of equations, polynomial equation, in one or many variables, and then we're going to consider it as an equation in the mod p world for a variable prime number p. And the question is, as we do that, how does the number of solutions vary? If we fix the equation and vary the prime number p, how does the number of solutions in the mod p world vary? And to talk about this, let me start with this very simple example. X squared plus 7 is congruent to 0, or x squared plus 7 equals 0. So we're asking about square roots of minus 7 in the mod p world for a variable prime number p, 2, 3, 5, 7, 11, and so on. And maybe I should point out that a minute ago I was considering congruence is modulo 7. Here I've got 7 as a coefficient. It may be an unfortunate choice. It's not playing the same role. Okay, well, let's look at this particular quadratic equation, x squared plus 7 equals 0. And here's a variable prime number p. And for the first few prime numbers, I've tried to solve this equation and written the solutions here on the right-hand side. I've left out 2 and 7 because they behave slightly differently. I think it would be easier to see the pattern if I leave out those 2 particular small prime numbers. Okay, so one obvious thing seems to be that there are either no solutions or there are exactly 2. I think that sticks out immediately. One can then ask, can you see the pattern? Well, I mean, you can ask yourself, can you see the pattern? And if you can't, maybe I can help a little bit by, here I have the same table, variable prime number p, and the solutions to the equation s squared plus 7 is congruent to modulo p, but I've added an intermediate table which is plotting p modulo 7. So notice I'm doing very different things. Here I'm considering an equation modulo a variable prime number p, and here I'm considering the variable prime number p in mod 7 arithmetic. And now it may be easier to see the pattern, I don't know. If I look at 3, there are no solutions to this equation. Every time that p is congruent to 3 mod 7, you will see that there are no solutions. Again, for 5, there are no solutions. Every time that p is congruent to 5 mod 7, you'll again see no solutions. On the other hand, for p equals 11, there are 2 solutions. 11 is 4 mod 7, and every time p is 4 mod 7, where else have we got it? There are 2 solutions. And in fact, this is the general pattern when we have a quadratic equation in one variable. And I think it was Euler who realized, so I have some pictures of some of these great mathematicians, Euler who realized in the year of his death, 1783, that this should be the general pattern. That when I have a quadratic equation in one variable, you can always get rid of the linear term. So if I look at an equation of the form x squared congruent to n modulo a variable prime number p, the number of solutions is either 0, 1, or 2. We didn't see the 1. That hardly ever occurs. It just occurs for a finite number of prime numbers p. So we can almost forget this possibility. The generic case is that there are either no solutions or 2 solutions. And then that's not so surprising and not so difficult to see. What is much more surprising is that when I fix the number we're trying to take the square root of, wherever there's 0 solutions or 2 solutions only depends on the prime number modulo which we are working, modulo 4 times n. And again, I want to say how surprising this is to me, that here we have an equation modulo p, and the criterion for its solvability depends on sort of the opposite thing, p modulo 4 times n. Well, Euler wasn't able to prove his conjecture, but Gauss did in 1796 at the age of 19. It's supposed to have been his favorite theorem. He called it his Theorema aureum, golden theorem. During his life, he gave 8 different proofs of it. And as I say, I want to stress how remarkable it is. It's the sort of first theorem you come across in an elementary number theory course, which still to me sounds is really rather surprising. And here is Gauss, who first proved it. And just as an illustration of so not only is this surprising, but it's actually, if you want to do calculations in this sort of area, it's actually extremely effective. It means if you ask how many solutions does x squared plus 7 have modulo 32,452,843 to choose a random prime of a certain length, it is a prime number. With a computer, it wouldn't take you long to run through the 32,452,843 possibilities, but I can do it in less than a minute without modulo 28. What I was supposed to take 4 times minus 7, plus or minus doesn't make any difference in this game. Modulo 28, the number of solutions to this equation won't depend on the prime modulo which we consider it. Modulo 28, 32,452,843 is the same as 3. So this equation modulo this large prime has exactly the same number of solutions as this equation modulo 3, the same equation modulo 3. And modulo 3, it's very easy to check all the possibilities. There are only possibilities for x as 0, 1, or 2. And if 0 squared plus 7 is 7, which is 1 modulo 3. 1 squared plus 7 is 8, which is 2 modulo 3. And 2 squared plus 7 is 11, which is, again, 2 modulo 3. So this has no solution, so this equation also had no solutions. Okay. Well, that's Gauss's celebrated law of quadratic reciprocity, which indeed Bob referred to in his lecture. I want to now ask, what about equations with more variables or even systems of equations with many variables? And I'm going to look at what's probably the simplest example. I'm going to look at a smooth cubic equation, I want to assume it's smooth, in 2 variables, x and y. In fact, I'm going to want it to be in the form a quadratic in y is equal to a cubic equation in x. These things are called elliptic curves. Doesn't matter so much. It's sort of the simplest example in more than one variable. And again, one can ask the same question. How does the number of solutions modulo p vary? And again, let me first make a couple of remarks. So I'm going to be talking about this quite a lot in this lecture. I'm going to write NP simply for the number of pairs xy modulo p that satisfies an equation like this. And one thing I want to I'll be needing is that NP is approximately p. This was proved by Hasse at the early 1930s. He proved that you might guess that this is approximately p because we've got p possible values to try for x. And each time we're going to get some quadratic equation in y which either has 2 solutions or no solutions. And you might hope that it's got about a 50-50 chance of having no solutions or 2 solutions, in which case the number of solutions would be, total number of solutions would be 2 times p over 2, which is about p. And indeed, that's what Hasse proved, that if I take the difference between this equation modulo p will have approximately p solutions. The difference between p and the number of solutions is bounded by twice the square root of p. We'll be coming back to that. Okay, well, to get a feel for what one might expect in this case of a greater number of variables, well, the first thing we notice immediately is that we're not in a case of a finite number of possibilities for the solutions. It's growing with p, so there are infinitely many possibilities of np, but we can still ask if there's some structure to it. So let me go back to my equation y squared plus y equals x cubed minus x squared, a specific example. We already looked at this modulo 7. Modulo 7, we saw that there were 9 solutions. I made a little table here. So n7 in my notation is equal to 9. Here the possibilities are x, the corresponding values of x squared minus x cubed minus x squared, and then I've listed the possible values, solved the corresponding quadratic equation for y, and listed the possibilities. This is very easy to do, and indeed, if you're bored already, you could spend the rest of the lecture on a scrap of paper trying to do the same calculation modulo some other numbers. I've done it for a few small primes. Modulo 2, turns out there are 4 possible solutions. Both x and y can be either 0 or 1. Modulo 3, again, there are 4 possible solutions. X can be 0 or 1, and y can be 0 or 2, and so on. I did a few more of these. While I did the by hand, I went up to p equals 13, where there are 9 solutions. And then, just to be convincing in a minute, I decided to do 2 more. I first of all gave up and asked my wife to help me do it on a computer at this stage, because I'm not very good with computers. I was rather pleased because I did it by hand before she had finished the calculation on the computer. I was less pleased when we had different answers, and on examination it turned out she was right and I was wrong. But anyway, those are the solutions for so modulo 19, there are 19 solutions to this equation, y squared plus y equals x cubed minus x. So, here I've recorded the result of my little experiment, numerical experiment. I've listed the primes across the top, and then because we know the number of solutions grows approximately the same rate as the prime p, I've plotted the error, the difference between p and the number of solutions modulo p, this little table. Now, so our question about generalizing Gauss's reciprocity law is to somehow ask, can we predict these numbers? Can we predict these numbers as the variable prime p? And the extraordinary answer is, one looks at the following infinite product in an indeterminate, which is traditionally written q. I take q times the product from n equals 1 to infinity, 1 minus q to the n squared, times 1 minus q to the 11n, all squared. And again, with the help of my wife's computer, you can multiply it out to, say, 20 terms in q. And here is what you get. And the extraordinary thing is that if I look, for the prime 2, the error was minus 2. If I look at the coefficient of q squared, what do I see? I see this same minus 2. If I look at the coefficient of q cubed, I see the same minus 1. If I look at the coefficient of q to the 5, I see the same 1. 7 gave the error was minus 2. If I look at the coefficient of q to the 7, I get minus 2. 11 gives 1 plus 1. 13 gave 4. Here I'm again getting 4. 17 minus 2. 19 gives 0. Q to the 19 doesn't occur in here. Again, a quite remarkable fact to my mind, because these two calculations had nothing whatsoever to do with each other, and yet we're getting the same numbers. And this was observed and proved by Martin Eichler in the mid-50s. He's a rather underappreciated mathematician. He started a number of fundamental observations. this. Well, one might ask how one generalizes this. If I took a different plane cubic equation, a cubic equation in two variables, is there something similar? And the answer is that there's something a bit similar, but not exactly similar. The fact that I got a product here is really rather special to this elliptic curve. It's not generally indicative of what happens. But there is some substitute which is at root much the same thing. And Taniyama-Shimura and then Wei conjectured in the 50s and then maybe in the 60s a bit that a very similar thing happens for any plane cubic equation. That if you calculate the number of points mod p, calculate the difference from p, this sort of error term, there is some pattern, some effective way for computing them using completely different notions. Now, I don't have time. I have some pictures of the principles in this conjecture. I should say that Taniyama first suggested something like this was true in a rather vague way. Shimura made that much more precise. And then Wei's name tends to be dropped from this these days. The reason I've included it here is that I wanted to emphasize that this was really an effective algorithm for computing these number of points mod p. And it was Wei who made that clear. Well, I'm afraid I am not going to be in this lecture be able to say anything very precise or anything at all precise about what this effective algorithm is. But I did want to say that it has to do with very different sort of mathematics. It has to do with symmetries. In this case, symmetries of some space, a plane space, but not the familiar space we live in, but something called hyperbolic space where things are curved in a strange way. In this case, symmetries of the hyperbolic plane. So I have here a diagram, a sort of drawing of the hyperbolic plane. Imagine sitting inside a disk, which you have, and it's tiled by congruent shapes. So you have to imagine that these little shapes out by the boundary are really, in this world, are just as big as shapes in the middle here. It's a sort of geometry where there's really a lot of space as you go out towards infinity. This hyperbolic space is perhaps best known through some of Escher's woodcuts. It was the Canadian geometer and group theorist Coxeter introduced hyperbolic space to Escher, who was rather inspired by it, and made a series of woodcuts based on the hyperbolic plane and the symmetries of the hyperbolic plane. Here is one of them, his circle limit 3. And as I say, I'm afraid all I can say about it is it's somehow the study of symmetries of this space which is giving the way of understanding the number of solutions to such an equation. It is, again, a very effective solution. People who are good with computers can implement it very effectively to compute these numbers very quickly. And to me, what really attracts me to it is the fact that these two things shouldn't have anything to do with each other. Here we're doing some algebra. We're doing algebra modulo a prime number p in finite characteristic. Over there we're doing some geometry and looking at symmetries. There's no a priori reason why those things should be connected. Okay, well, this was finally proved in 2001, the full conjecture, following the breakthrough by Andrew Wiles in the early 90s, and partly jointly with myself. And there is also, lost. And in a sense, there's no real reason to restrict to cubic equations in two variables. We now imagine, following Bob's insights, that something similar, something of the same sort of nature should be true for any number of equations, in any number of polynomial equations, in any number of variables. And again, the answer should involve symmetries of some sort. Well, for completeness, I also have Bob's photograph, not that we really need it. Okay, so that is really what I wanted to say about reciprocity laws, but I did also want to talk about what one might call density theorems or questions of distribution. So far I've been asking for a sort of a precise formula for the number of solutions of such an equation. And I've said that we believe that one exists in great generality, and in these few rather simple special cases, we now have theorems that not only appear deep, but actually, as Bob was saying, answer old questions like the key to proving something like Fermat's last theorem. But one might ask the slightly different but related question, if instead I ask for an exact formula for each p, I ask just how does the number of solutions vary as the prime number p varies? So if I go back to my quadratic equation in one variable, x squared plus n equals 0 modulo p, for what fraction of prime numbers, we know it has either 0 solutions or 2 solutions, for what fraction of prime numbers does it have 0 solutions, and for what fraction does it have 2 solutions? Well, there's an obvious guess. Half the time it has, you might guess, half the time it has 0 solutions, half the time it has 2 solutions, and indeed that's what Dirichlet proved in the first half of the 19th century. To be careful, Dirichlet gave a slightly curious meaning to half. If you take perhaps the most natural meaning of half, if you just count up to the first x prime numbers, and you look at the fraction of those for which this has 2 solutions, and then let x go to infinity, does that tend to a half? The answer is yes. Dirichlet didn't quite prove anything as strong as that, but by the end of the 19th century, that too was known. But I think basically the sort of idea was due to Dirichlet, and it does use Gauss's quadratic reciprocity. He doesn't argue directly with